Hey folks, I hope everyone's doing well. I want to do a proof of the sum law using the epsilon delta definition of the derivative, using the epsilon delta definition of the limit. So in order to do this, we're going to have to make use of the triangle inequality that you talked about on the previous page of this document. And the triangle inequality says that if you have the absolute value of u plus the absolute value of v, that this is always going to be greater than or equal to the absolute value of u plus v. And you may have trouble remembering that expression, so it's really helpful to remind yourself that this has to do with the sum of two sides of a triangle is always greater than or equal to the length of the third side. So if you remember that, that helps you remember that triangle inequality. So let's remind ourselves real quick of what the sum law originally said. It said, suppose the limit as x approaches a of f of x equals, and let's say it exists, so we'll say it equals m, and the limit as x approaches a of g of x equals n. Then what can we do? Well, we can do many things with this, but for the sum law, we're going to say that the limit of the sum of these two functions as x approaches a is the sum of the limits. So let's write that out. The limit as x approaches a of the sum of these two functions, f of x plus g of x, is equal to the limit as x approaches a of the first function, so that's the limit of the first, plus the limit of the second. And so how would we actually compute that? Well, you could say that's m plus n. So let's go ahead and prove this. So rather than doing the scratch work for this, I'm just going to jump straight into the proof. And so this is why it's a little bit different than the ones I'm asking you to do on your own. And so for this, we'll just go ahead and say, let epsilon greater than 0 be given. So we're assuming we've got some tolerance that we want to get our y values within. So let epsilon greater than 0 be given. And before I go to set what I want my delta to be, I need to do a little bit of preliminary work. So since the limit as x approaches a of f of x equals m, we know we can find a delta 1 so that the distance between f of x and m can be made arbitrarily small. It can be made as small as we wish, and here you would normally expect to write epsilon there, but I'm going to put epsilon over 2, and that's just so that the proof works out nicely. So for example, if our original epsilon was, some small number like 0.008, then if that's our epsilon, then our epsilon over 2 would be 0.004. Okay, so we're taking half that. Well, we know that can be done because we know that the limit as x approaches a of f of x exists. Okay? So we know that that can be done as long as 0 is less than the absolute value of x minus a is less than what I'm calling delta 1. So the distance between f of x and its limit can be made as small as we want as long as we get within some delta strip, which I'm calling delta 1 here. And the reason why I'm using delta 1 is because I'm actually going to have 3 deltas in this problem. So the next part is exactly the same. We're going to say that since the limit as x approaches a of g of x equals n, we can find a delta 2 so that the absolute value of g of x minus n, that's the distance between the y values of g of x and what we think the limit is, can be made as small as we want. In this case, I'm also going to pick epsilon over 2, provided the absolute value of x minus a, and I should put as 0 is less than the absolute value of x minus a is less than some delta 2. Okay? So what we're saying here is, do you want to make the distance between g of x and what we think the limit is as small as you want? Yes, you can do so, provided you pick domain values within that delta strip. Okay. Oops, I lost a little bit of that writing there. Absolute value and delta 2. Great. So now let's return to the original proof, which is we were trying to prove this sum law. We were given an epsilon, and so here we go. Here was the let epsilon greater than 0 be given, and now we will say set delta equal to, so this is a new delta, and delta is going to be the minimum of delta 1 and delta 2, the minimum of those two. So this might be a number, this is some small quantity, this is some small quantity. One of those two numbers is going to be smaller than the other, or if they're the same, you just go ahead and give that number. So our delta for the proof of the sum law is simply the smaller of the two deltas of the underlying limits. So that, and this part should look a little bit familiar, so that whenever 0 is less than absolute value of x minus a, which is less than our delta, we have, and now we're ready to do the proof here. So we're going to start out with the distance between the function, which is f of x plus g of x, and what we claim the limit is, and we claim that the limit is the sum of those two limits, so it would be the sum of m and n, so I'll put m plus n. So our goal is to show that this thing is eventually less than epsilon. That's our goal. Okay. Well, what we can do is inside these absolute values, we can do some rearranging. So we've got the absolute value of f of x minus m plus g of x minus n. So all I did here was inside the absolute value, I rearranged these terms. I wrote f of x minus m, and I wrote g of x minus n. Okay. And so what have I got here? Well, I've got an absolute value with a sum of two expressions inside of that. And now I'm going to use that triangle inequality that we talked about, and we're going to think of this sum sitting inside the absolute value as the third side of a triangle. And what do we know that third side is? We know that that third side is always less than or equal to the sum of each of the individual sides. So that third side is the sum of this expression and this expression, and we know that that's going to be less than the absolute value of f of x minus m plus the absolute value of g of x minus n. This was right here by the triangle inequality. Okay. Then we know that this expression right here can be made as small as we want as long as our delta, or as long as the distance between a and x is less than our delta 1. So we can make this less than epsilon over 2. That's what we wanted to do. We said we go ahead and pick the delta 1 that ensures that the distance between that y value and what we think and what its limit is less than epsilon over 2. We can do that as long as our distance between x and a is less than delta 1. Plus, and then likewise, think of that as the distance between g of x and what we think its limit is, and we can also make that as small as we want, in this case epsilon over 2, as long as our x values come from within that delta 2 strip. And why does all of this work? This works because our choice for delta for the overarching problem was the smaller of those two deltas. Okay. And so this expression right here, epsilon over 2 plus epsilon over 2 is equal to epsilon, and there we've proven the sum law. So folks, take a look at that, and please let me know what your questions are.